Look up on a bright sunny day, and you'll see a clear, beautiful blue sky. But wait for the sun to set, and suddenly the sky is a canvas of reds, oranges, and pinks. This daily transformation is not just poetic, it's scientific. So, why is the sky blue? And why does it turn red during sunset? The answer lies in the interaction between sunlight and the Earth's atmosphere, and it's one of the best examples of everyday science happening right above our heads. Let's start at the beginning. Sunlight, though it appears white to our eyes, is actually made up of many colors. You can think of it like a rainbow hidden in plain sight: red, orange, yellow, green, blue, indigo, and violet, all blended together. This was proven by Isaac Newton when he passed sunlight through a prism and split it into a spectrum of colors. Now, as sunlight enters the Earth's atmosphere, it doesn't just pass straight through. It collides with molecules of air, dust, and water vapor. When light hits these small particles, it scatters, and this scattering isn't the same for every color. This is the key. Light colors like red and orange have longer wavelengths, which means they pass through the atmosphere mostly unaffected. But blue and violet have shorter wavelengths, which makes them scatter more easily when they hit air molecules. This type of scattering is known as Rayleigh scattering, named after Lord Rayleigh, who explained this effect in the 19th century. So, during the daytime, when the sun is high in the sky and its light travels a relatively short distance through the atmosphere, the blue light gets scattered in all directions. That scattered blue light is what we see when we look up. It fills the sky with a blue glow. Even though violet light actually scatters even more than blue, our eyes are less sensitive to violet, and some of it gets absorbed by the ozone layer. That's why the sky doesn't look violet. Here's a real-life example. Think of a room filled with fog. If you shine a flashlight into it, the light gets scattered, and the beam appears wider and softer. That's what the atmosphere does to sunlight, spreads and softens it, especially the blue part, making the whole sky glow blue. Now let's talk about sunsets and sunrises. When the sun is low on the horizon, its light has to travel through a much thicker layer of the atmosphere to reach your eyes. In this longer journey, most of the blue and violet light has already been scattered away and redirected elsewhere in the sky. What remains is the red, orange, and yellow light, which continues traveling through the atmosphere with less interference. That's what reaches your eyes directly at sunrise or sunset, the longer wavelengths that weren't scattered away. The result? A sky painted with warm, rich hues that are beautiful, soothing, and entirely natural. And here's the fun part: pollution and dust in the atmosphere can enhance these colors. That's why sunsets look more dramatic in cities or after volcanic eruptions, because particles in the air scatter light differently, creating deeper reds and purples. Right pointing finger emoji. If this breakdown of the sky's colors amazed you, please take a moment to like this video and subscribe to the channel. We've got a universe of everyday science to uncover, right from your window to the stars. Now, why is understanding this important? First, it connects you to the world in a more meaningful way. The sky isn't just a background, it's a visual storybook of light, physics, and atmosphere. Knowing why it's blue during the day and red in the evening helps you appreciate the science that surrounds us daily. Second, this knowledge is useful in photography, filmmaking, weather prediction, and even designing lighting systems. Artists and cinematographers use warm colors to depict sunsets for emotional effect, and now you know there's real physics behind that color choice. In science and education, this concept introduces learners to light waves, scattering, wavelength differences, color perception, and atmospheric science. It's a stepping stone to understanding much bigger topics like climate change, space science, and optical technologies. Also, Rayleigh scattering isn't just limited to Earth. It's why Mars has pink skies, and why the sky of Uranus would appear teal. This concept plays a key role in how we study the atmospheres of other planets and distant exoplanets. Scientists use similar principles when analyzing light from far-off worlds to determine what gases make up their skies. Even in health and safety, the understanding of how light interacts with particles has applications in UV protection, lens design, and visibility on roads during foggy or dusty conditions. It helps engineers design more efficient optical instruments and weather satellites that rely on how light behaves in the atmosphere. And let's not forget aviation. Pilots and air traffic control experts monitor the color of the sky, especially during dawn and dusk, as a way of judging visibility and weather patterns. Red skies in the evening really do signal stable air, something sailors and farmers have relied on for centuries. So the next time someone asks, "Why is the sky blue?" you won't just say because it is. You'll know that it's because of Rayleigh scattering, the special way light moves through air, and how your eyes are finely tuned to receive that scattered glow. And when the sun sets, you'll see more than a pretty sight, you'll see wavelengths stretched across space, a brilliant goodbye from the sun as it dips below the horizon. That's the beauty of science. It takes the ordinary, and makes it extraordinary.